Okay, so hey guys, it's Quinston, and today we are going to talk about the Manacher's algorithm. So in the previous videos, we found how to calculate the longest palindrome substring, but the methods that we used, well, they were incredibly difficult for the computer to process. They had incredibly high complexities, and well, they were difficult. This is because the complexity of the algorithms was incredibly high, so we had to find other methods, which we are going to cover in this video. This algorithm finds the longest palindrome substring in big O of n complexity, which is incredibly useful for us. So if we have a string like AB, AABC, that's what we are going to experiment on, the first step is called separation. In the separation method, you basically place symbols in between the characters to make sure that even if the strings are of even or odd character lengths, odd characters, even, whatever, it wouldn't matter, okay? It wouldn't matter. We are going to use the separation symbols of hash, so pound, hash, whatever. So let's go ahead and do it. And then we get the string hash A, hash B, hash A, hash A, hash B, hash C. Try saying that with a mouthful. So let's talk about another property. Let's talk about mirroring. As you can see, we have two rows here. One row is a modified string, and the other row is a row of numbers, which is actually an array that we will denote by P. If you observe closely, the numbers in P correspond in some way with the string. I don't know what way, but there's some way. Check the first character B. Check the first instantiation of B. The corresponding value in P for B is 3. If you expand the string towards the left and the right from B, expanding here means trying to find the palindrome which centers at B. So here that center will be basically collecting 3 characters in the left and 3 characters on the right, and that gives you a palindrome of hash A, hash B, hash A, hash B, with B at the center, of course. If you look closer, a little bit closer, a little bit more closer, the numbers on the left of 3 and the right of 3 are to an extent mirror images of each other. Does that not blow your mind? This is the holy grail on top of which the entire algorithm is built. But is this a coincidence or a tried and tested property? Well, it's a bit of both. The entire of P, the array P, okay, is created in such a fashion by storing the values which we find by expanding and mirroring in the corresponding location in P. Let's take an example for better understanding. Of course, nobody understands without examples these days. We have our string here, okay, which is altered by the symbols, hash hash. We have an iterator which is going to go over all of the characters in the string one after the other, and we also have an array at the bottom which is going to store all the numbers that we come across in the program, which is basically denoted by P, as we talked about earlier. And also we have the mirroring line. The mirroring line, as you see, the dashed line, is the line along which the current mirroring process is going to exist. We're going to check the mirroring process by using that mirroring line. Pretty interesting, of course. All the values are set to 0 initially, and so let's begin our quest to find the longest palindrome substring. The first letter doesn't really have a lot of prospects here. Its value is bound to be 0 because there are no characters on the left hand side. Moving on to the next character, we encounter A. Now expanding on the left and right gives us a value of 1 because there is one character on either side of A, which when combined with A gives us a palindrome, which is hash A hash. Hence, we store 1 in our array. Now that we have found a palindrome, we will update our mirror line and make it point to A, okay? We also set left and right markers to indicate where the palindrome begins and where it ends, corresponding to the current mirror center. We move to the next character. Once we move, we realize that the current character and R are the same, okay? The mirroring property does not work well for the start and end characters of the palindrome. It just doesn't. Usually because by being at the edges, at the ends, and starting, their mirror counterparts are always mostly values of 0, which anyway is the default starting value, so there is no use in wasting processing power over them. We directly move to expanding them on the right and left, ignoring their mirror. In this case, you can't even expand it as it has an A on the left and a B on the right, effectively ending its career of being a palindrome. I'm sorry, man, you are not a palindrome. Next, we move on to our first B. The B is outside our scope of mirroring, and hence we can't really do much with the property of mirroring. So we proceed to expand it and get the palindrome hash A, hash B, hash A, hash. Now that our pointer is outside I, we can effectively update our bounds of the markers L and R and the mirror line itself. And that is what we do. The next character is the first one which fits the bill for applying the mirror property on. When you think about it, the value here has the maximum potential to be an index of r minus index of pointer, which is 2, right? The index at r minus the index of pointer, you get that counted, you get a value of 2. This is because we are mirroring from 3, right? The character has a value of 3 at the mirroring center. So the maximum value that it can hold on the right hand side is 2, which is 3 minus 1, which is interesting, right? It makes sense, yeah. But the value which we will choose is the minimum between the mirror value, which is on the left hand side, and the index of r minus the index of pointer, which is 0 versus 2. So which is smaller? As a result, we choose 0 because 0 is smaller. We put 0 in our value array, that is p, and try to expand it, but it doesn't form any palindrome. And hence that validates our hypothesis. We can't update any of our parameters here as our pointer is still bound by r and l. The next step is moving to the next character. We use the same method as above to calculate against either using the mirror image of that value of index of r or index of pointer, and you subtract those, right? You subtract the index of r minus the index of pointer. We realize that both are the same, and so we place one of them at the index. It becomes 1, right? We still can't update any of our parameters here, as you know, the mirror line and stuff, as our pointer is still bound by the r and l. Now we sit on the location of r. We said earlier that the mirroring property does not work well for the start and end characters of the palindrome. The same applies here. So we just set it to 0 and start expanding. After expanding, we get the value of 4, which is crazy. This means that the string we encounter was hash b, hash a, hash a, hash b, hash, which has a length of 9. 4 plus 4 plus 1. We set the value and now must decide whether to update the mirror line or not. So when we do officially update the mirror line, I don't know, do we update it when the pointer, the index of the pointer plus the value of p at the index of the pointer is greater than the index of r, which means that we need I plus the value stored at p of I to be greater than r, and that gives us the value if it is, you know, extending beyond past r, and then only then have we to set new bounds for checking the new characters. If the palindromes that we found never expanded beyond r, there was no need to update the mirror lines because I will always be less than r. Then it makes sense, right? If your pointer doesn't extend beyond r, why in God's name are you trying to do that? It makes no sense, right? Moving to the next character, we find an obvious use case for using the mirror values. Expanding doesn't give us anything, and we move to the next character. We apply the same principles here and we get the same result. Next, we face a new challenge. The value of r minus the value of the index of r minus the index of the pointer is less in this case, as opposed to the previous case, than the mirror value. And we swore to always use the minimum of them both. Hence, we use index of r minus index of pointer, that value, and that is the correct one, as expanding doesn't give us anything. Hence, that is how you finish up with the last c expanding to 1 and the last character is expected to be 0 because 0, you know, there's no character to the right of it. And that is how this algorithm works, you know, and then basically you go through the entire p and find out what value is the maximum, and you basically get the value of what you want at the end, and that's the palindrome. This algorithm is truly not straightforward, so let's take a look at the code. So this is the code for the Manacher's algorithm. It starts with you pre-processing the string because you want to add all of those hashes. So in the pre-process function, you basically take a character array, which is a string. You find the length of that string. You basically create a string which is 2 times plus 1 the length of that particular string because, hey, you want to store those hashes along with the characters. So if you calculate, the hashes plus the characters are going to be greater by a margin. They're going to be greater by a margin. And plus, I also want to have a definitive space to store all those characters. Next, I also have a temp pointer because I don't want to use my original pointer to basically go through the entire list. I want to use a temp pointer because the temp pointer will basically act as a temporary pointer without me ruining the pointer of my array. And this is in C++, obviously. So I'm using pointers over here. I'm basically setting the first hash over here and temp plus plus, and basically I'm going through one by one all of the hashes, taking a character at a time, taking a hash at a time, character hash, and that's what I'm returning. I'm returning the pointer to the string which I just created, and that's pretty simple. So once we are done with the pre-process function, we take the length of that particular string, take the length and basically put it in this variable called length. Then we define the star p row, the row which will store our palindrome numbers. You know all the numbers we talked about below in the second row? Yeah, those numbers are going to be stored over here in the star p array. The next part is we define two variables. One is the variable c and one is the variable r. Now these two variables are very important. We don't define L. If you observe, we don't define L because we don't need it. We don't need to find L, because whatever L provides us, we can actually calculate by using something like this I mirror expression. So C is basically the mirror line. If you see the presentation, the mirror line is basically where C will be pointing to. That will act as the index of the mirror line, and R will be the index of where we are going to end our bounds on the right hand side. Okay, now let's start iterating through the entire string one by one. So this is the for loop, the iterator loop, which is going to help us iterate through the entire string. We have the I mirror. Now what is I mirror? I mirror is basically going to be the value that is going to be the mirror index of the value that I'm currently pointing to. So if I'm pointing to, say, the mirror index is C, and I'm basically at a character which is to the right of C, and basically I want to find the mirror index, the index of the mirror character. This is what I'm going to use. C is basically the mirror index minus I minus C. So I minus C will give me that value which is the mirror index. That value I'll subtract with C, which will reduce the index by that amount, and that will basically give me the mirror index of I underscore mirror index. Next, I'm going to check if R is greater than I, and we have done this numerous amounts of times in the presentation. If R is greater than I, if the right bound is greater and the I is less, then the character which I'm iterating on has a lower index than the R. The R is out of bounds. If that's the case, then I'm basically going to pick the minimum of R minus I, or because R minus I can obviously be the maximum value which can be attained by that particular character in the array P. Or I'm going to choose the P of mirror. So whichever is minimum, I'm going to choose that, and then I'm going to expand. So this while loop is basically for expansion. What it does is it basically takes your I, adds 1 to it, and then takes the value which P of I stores, basically because P of I is already having that amount of characters. So if you have P of I equal to 2, the array P already knows that you have 2 characters on your left and right which form a palindrome. That's what I'm doing over here. 2 characters plus 1, because I want to extend my bounds. I want to expand my bounds by 1. And then I basically do P of I plus plus if I found that both of them on the plus 1 and the minus 1 are the same. So that basically gives me a palindrome, and that's why I use P of I plus plus. Pretty simple stuff. Next, I'm going to update my C location and my R location. Now, what are the conditions for this update? Basically, the conditions are very simple. Is that if you extend your bounds, if I plus P of I is greater than R, okay? If you extend your bounds, if the current index at which you are extends the bounds beyond R, then you basically have to update your variables, and that is exactly what we're doing here. We saw all of this in the presentation. It's all here. C will be I and R will be I plus P of I, because you know how far R is supposed to be from the center, the mirror center. And basically I'm just printing out C. I probably don't need this here right now. All the code will be in the description, guys, so don't worry about this. Next, what I'm gonna do is I'm basically going over the entire length of P and picking out the largest value of P. And once I get that value, I'm gonna post-process. Post-process basically means that I'm going to remove the hashes of the substring which I get. Substring is the string which I get from the center minus max length and center plus max length. So max length minus max length plus, you basically get the palindrome of that substring, and that's about it. The post-process function is also pretty simple. It basically just whenever it finds like a hash, it doesn't include it, and everything else it includes into the string and returns it. Pretty simple, guys. The code is in the description. Thanks for watching. I hope you found this video helpful, because the Manacher's algorithm is, however much people deny it, it is kind of convoluted, a little complicated, but yeah, I hope this helps, and thanks for watching, guys. I will see you in the next video. Please like, share, and subscribe, because these kind of videos are very hard to make. You have to think about a lot of things, and yeah, I really appreciate a subscribe, and I really appreciate a like, and I really appreciate you sending me messages, commenting, and all that good stuff. So later, guys.